Okay, so the nomogram or nomograph, as it's known, can be a very challenging instrument for students who are beginning in forensics to master. So if you tried to do it from reading the text alone and you struggled, don't worry. Hopefully after this video, you'll feel very confident about this skill, which again is more historical than anything else. Nowadays, it's mainly just plugging data into a spreadsheet type software and getting an output for the postmortem interval. But this was an important historical development, and it's still a skill that I think a lot of you will appreciate once you get the hang of it. Okay, so we see on the right-hand side of the slide the standard temperature time of death relating nomogram. It's also referred to as a nomograph in the text, so we'll use those terms interchangeably. We see that it has a series of temperatures and kilogram masses, and it looks a little off-putting maybe, but once you get the hang of these things, they're not just easy, but fun. In order to solve nomogram problems, you have to know four pieces of information. So first of all, we'll address the rectal temperature of the victim, and you can see along the left there it says degrees C rectum down at the bottom. We also need to know the ambient temperature, the temperature around the body, and that's going to be on the right-hand side of the nomograph, and you see ambient degrees C up along the right. Victim's mass, the body mass in kilograms. Since we're in the US, we often have the body weight in pounds, so we'll talk about converting that value. And finally, there's the possibility of corrective factors. If you look up along the top arc there, you see the terms using corrective factors and standard, and then in parentheses naked still air. So most of this modeling for the body heat loss was done with naked bodies and still air, which is a fairly common way to find them. The perpetrators remove the clothing and any other chances for physical evidence, they hope, although usually they do leave some fibers or something behind at least. But that's mainly to frustrate the forensic scientists and make it more difficult to solve the crime by having the body naked in still air. Oftentimes, however, the body has clothing or is wet or there's moving air. There's other things to worry about, and we'll talk about that when we get to example 2. Okay, so let's get right down to business and work our first example together. In this case, we're going to follow a victim with a rectal temperature of 30.0 degrees Celsius. If you're still getting used to Celsius, just remember normal human body temperature for a healthy living human is 37.0 Celsius, so quite a bit lower, and obviously this person has been dead for a little while at least. The ambient temperature, the temperature around the body in this example, is 15.5 degrees Celsius, so that's cool, but again, not unreasonable for, say, autumn in the southern tier of New York. The victim weighs 220 pounds, and the victim was found naked in still air. So for this first example, we're taking it easy, and we're just using that naked still air standard set of conditions for solving this nomogram problem. The way I tend to approach a nomogram problem is to embrace my inner child and get right to connecting some dots. So if you recall from the previous slide, we said that we had a victim rectal temperature of 30.0 degrees Celsius. So I have the rectal temperature blown up here, which appeared on the left-hand side of the handout. So there it is. I put a little mark, a dot, an X, whatever you want to do there, right at 30. So right on the line. Notice each hash mark would increase or decrease by 0.5 degrees Celsius. So for the rectal temperature, we start at 0 down at the bottom and we work our way up. On the right-hand side now we have the ambient temperature. That's our other dot that we'll need to connect now that we have a dot there on the rectal temperature. And this time we had an ambient temperature in this first example of 15.5 degrees Celsius. So notice I'm just one hash mark below 15. In the case of the rectal temperature, the temperature increases as you go up. Here with the ambient temperature, it actually increases as you go down. And so we see just above 0, there's that minus sign to let us know those are negative degrees Celsius temperatures. And then below 0, you see the plus sign to remind you that as you go down, each hash mark represents a half a degree Celsius. So I wouldn't be right on the 15 hash like I was on the 30 because I'm not at 15.0, I'm at 15.5. I need to go down 1 for the ambient temperature. Okay, so now that we have those 2 points, the rectal temperature at 30.0 degrees Celsius and the ambient temperature at 15.5 degrees Celsius, we can go ahead and connect the dots. Use a straight edge, a ruler is preferred, and go ahead and draw the straightest line you can that starts at 30.0 and runs through 15.5. All right, once you've got that down, we'll talk about the next step. Hopefully you noticed that there already was a line on the nomogram. There was that first line there, that dark line, and when we drew our line, which I have is in blue here to highlight it, we crossed that existing line, and I put an X there on the screen where we crossed. So that crossover point is the first point of our second line. Notice also there was the existing crosshairs there. That's our other point. So now that we've drawn the first line and it crosses that existing line and we have the center of the crosshairs highlighted, we're ready to draw a second line. This is where students tend to make a mistake. They draw the first line just fine, and then they forget what to do. They try to read off of that graph with the first line. No. The purpose of the first line is so that you can draw the second line. It's the second line that's going to get us to a post-mortem interval. So go ahead and connect those dots. Okay, so drawing the straightest line we can that goes through those 2 points, the center of the crosshair and the crossover point there where the blue line crossed that existing black line. And notice I carried all the way up to the top arc where it says using corrective factors. That's just to play it safe and make sure that we get where we need to go in terms of the body mass. Now we had a victim body weight of 220 pounds, and notice the highest arc on this nomogram is 200. So we're in trouble, right? Is the person too heavy for a nomogram? Not at all, right? We had to be careful about that when I mentioned it. Because we're in the United States, we tend to deal with body weights in pounds, but of course, being in science, forensic science, like all the sciences, deals with the System International, which is mainly the metric system of measure, and so therefore we're looking for kilograms. So that's why we can't find a 220 arc, because we're not looking for pounds, we're looking for kilograms. So let's talk about how we do that conversion from pounds to kilograms. Now the basic information here is that 1 kilogram, exactly 1 kilogram actually, I'd say 1.00 here just for purposes of having the right number of digits in the problem. So 1.00 kilograms equals 2.20 pounds. So it makes no sense to me why we would not embrace the kilogram system. It's the best diet you'll ever go on because your body weight will drop by more than half instantly. You don't have to do any diet or exercise. It's really remarkable. So I'll always provide that relationship if you were to work a nomogram problem on the exam. So you would expect to see the temperatures in Celsius like you'll need them, but expect to see the body weight in pounds, and also expect to see this conversion factor that 1.00 kilograms equals 2.20 pounds. And hopefully you remember that that means you'll be dividing the body mass, body weight rather, in pounds by the 2.2 pounds per 1 kilogram to get the body mass in kilograms. So we see I picked a nice easy body weight here, 220 pounds. When I convert, I multiply it by 1.00 kilogram over 2.20 pounds, I end up with exactly 100 kilograms. So now I can go back to the nomogram, and certainly there was a 100 arc that I could read there for body mass. Okay, so there it is. I've blown it up so that we can see it really well. And if you look, so the 100 number is just above the arc that corresponds to the 100 arc. If you forget, go ahead and look, and you see that 200 sits just above the last arc. So that's how you remember that the body weight there is, or body mass, I should say, is just above the arc that it corresponds to. So if we look here, you can see the number 12, and then you don't see anything again until 16. Well, each of those hash marks that we see on the way from 12 to 16 represents 1 hour. So we go from 12 to 13, which is not marked, to 14, which is not marked. Then just after my circle is 15, and then finally we get to 16, which is marked. So based on how my line fell, I'm just beyond the 100 arc at the hour 14. So I'm just a little beyond 14. Maybe your line's a little before it, or maybe it's dead on 14. Again, I do allow some tolerance. Usually I give a half an hour either way, or you would give a half an hour either way, say on a multiple choice test item. If yours doesn't exactly line up with mine, or if mine doesn't line up with yours, we do have some tolerance there, because when you draw the lines, it's tough to get them right exactly where they connect the 2 points. Okay, so based on the fact that I'm just a little over 14 hours, I'm going to say that this person died at with a postmortem interval of about 14.1 hours. So I've just estimated that final place to be a little beyond the 14 hours for the 100 arc, so we'll call it 14.1. So we still need to take into account that we can't know exactly to that level with something like a nomogram. When a victim's been dead for that length of time, there's a chance that based on how the conditions were, perhaps they've been dead not quite that long, or possibly even longer. So we're going to have to talk about how we deal with that in our next part. All right, so we mentioned earlier that we have those corrective factors up along the very top, and then underneath it, it says standard, which was naked in still air. So this time we had the body found naked in still air, so we're using the standard conditions, but we still have error inherent. And notice in this part of the nomogram, it actually didn't matter because either way we have 2,8, whether we're using corrective factors or not. So what that 2,8 is has to do with the fact that just like the rest of the world is using kilograms, and in forensic science we also use kilograms, even though in the standard United States units we use pounds, we also tend to put a decimal point where the rest of the world puts a comma, and vice versa. So that 2,8 is really 2.8 hours. And if you look along the very top where it says permissible variation of 95%, then it says plus or minus hours. That's the number of hours that we're looking at here for our first example. So as I said, we're looking along the bottom because we were standard conditions here, although it didn't matter in this region of the graph. Either way, it's 2.8 hours. So the actual postmortem interval, and again, an interval is a range of numbers, so that's good. We wouldn't have an exact value for a postmortem interval. We'd have a range of values. So here it's that 14.1 that we read off of the 100 arc on the graph. But it's plus or minus 2.8 hours. And that's an acceptable way to show the postmortem interval. The other way you might see it is to actually add and subtract those 2.8 hours from that 14.1, and we would see that our postmortem interval range, this victim could have died as little as 11.3 hours ago or as much as 16.9 hours ago, based on the permissible variation here in this nomogram. So there we have it. We were able to solve example 1 for a PMI, and hopefully you're feeling very comfortable and confident about the nomogram. Let's go ahead and try a second example just to make sure you're understanding these concepts. Okay, so here we are in example 2. So now we have a rectal temperature much lower, 22.5 degrees Celsius. Our ambient temperature is a little higher here at 17.5 degrees Celsius. In this case, our victim weighs 180 pounds, and this time the victim was found wearing one thin layer of clothing in still air. So we're not at standard conditions anymore, right? We're not naked. We have that one layer of thin clothing. So we're still air, well, that's good, but we do have to account for that clothing. So we'll worry about that when the time is right. Let's have our fun, and let's do the fun part first. Okay, so just like in example 1, we're going to find those values. So remember, working up is how we go up in temperature on the rectal side. So 22.5 is right there midway, and the ambient temperature of 17.5. So if you find 15, then count each small hash as 0.5. So 15, 15.5, 16, 16.5, 17, and then finally 17.5, right where we show it on the screen. Okay, so when you connect those two dots, we should end up with this line that we see. Notice that it's passing that existing line much further down. So we're going to end up at a further down region in the nomogram. So that suggests that, like our much lower human body temperature in this example, that there's been a longer time since death in this example. And just like before, now we end up with two new points, the center of the crosshairs and then the place where we cross that existing black line with our new blue line. So you know what to do. Time to connect the dots with another line. Okay, so notice now we've drawn our second and final line. This is the one that we'll actually use to determine the postmortem interval here. Notice a couple of things. First of all, there is a 180 arc here, so don't get confused. We're just about at the midpoint between 70 and 75 hours, 70 and 80 hours, right around 75 hours on the 180 arc, but of course, we don't want that arc. That's the kilogram arc. We're dealing with 180 pounds. So next up, we're going to have to do that conversion to figure out what the time really is, and it's not 75 hours, not even close. So the other thing to note is we end up in the region now where the using corrective factors value is 7,0, really 7.0 hours. Even without corrective factors, 4,5, which is really 4.5 hours. So there's much more error inherent now that the victim has been dead longer, and we're into this further region of the graph compared with early on at the left end of things that was 2.8 hours either way. Now there's, first of all, a big difference between corrective factors and naked and still air, and even naked and still air is significantly longer error compared with earlier in the graph. Okay, so there we have it, a reminder that 1.00 kilograms equals 2.20 pounds. So in this case, we have a victim that weighs 180 pounds. So when we convert that into kilograms, effectively dividing by 2.2, we end up with a value of 81.8 kilograms. Now there is no 81.8 kilogram arc on the nomogram, so instead we have to consider, first of all, are we really done? And I do try to make things work out close to perfect. So that's the first question to ask yourself is, did I do something wrong? And I meaning you in that case. The second question is possibly, did I do something wrong? I meaning me, the instructor. So in this case, we just have overlooked one more thing. So we're not going to round down to 80 kilograms. Rather, we're going to look at those corrective factors that we've ignored up until now. Okay, so there's our enlarged image there of the graph, and you see if we were to round down to 80, because we're certainly closer to 80 than to 90, what we'd end up with is something like, I don't know, 29 and a half hours postmortem interval, plus or minus the 7.0 or 4.5. We'll see which one in just a moment. But again, that you want to make sure that that's right, because if we should be on 90 instead, well, then we're beyond 30 hours. So that's a big difference to be just about at 29 hours versus to be just about at 33 hours. So let's see how we end up with a more exact mass by remembering the conversion factor. Okay, so there it is, a reminder that we did not find this victim naked in still air, but rather with that one thin layer of clothing in still air, so we have to account for the appropriate corrective factor. That's why our mass didn't work out very nicely here in this example. In the real world, things rarely work out nicely. We'll talk about that at the very end. So if you look at the backside or the second page of that nomogram for temperatures, ambient temperatures up to 23 degrees Celsius, which is available as a download on Blackboard in the Chapter 2 folder, you'll notice that the backside has that table of corrective factors. So this would be page 2 of the file. I show the full page over to the left, and then I have increase the size of the table itself, which is the empiric corrective factors of the body weight. So notice along the left-hand side is when you have dry clothing or dry coverings in air. On the right-hand side is when you're wet through either the clothing or the covering. So there's a wet body surface that typically causes the body to lose heat a lot faster than a dry body. So you notice we have corrective factors less than 1 for many of those cases. In the case of having clothing on that's dry, it typically causes the body to act like a heavier body mass individual. And so just think about that. If we're modeling this based on a naked body in still air, it's really the fat that we're relying on to slow down the heat loss. So a heavier individual, all other things being equal, should be able to hold his or her body heat for longer than a thinner individual because the heavier individual has more body fat. So if you think about clothing like additional body fat, at least in the case of dry clothing, that's why we have a corrective factor that is larger than 1, because at least if it's in still air, those thin layers of clothing or thicker layers of clothing or bedspreads cause the body to lose heat at a slower rate, and therefore the body's acting more like a heavier body weight individual. On the other hand, if we look at that wet throughout, that's going to, the water there is going to dissipate the heat much faster, and that's where a heavier individual is going to lose heat at a rate closer to a much lighter individual, because the water is going to act as a heat sink and really cause the body to lose heat very, very quickly compared with a dry body in still air. So the particular conditions we're looking for here in example 2 is one thin layer of clothing in still air. So I've underlined there, it doesn't really seem to matter too much whether it's 1 or 2 thin layers. Either way, as long as you're in still air, the corrective factor is 1.1. So just be careful. If you go up 2 from that entry, you have the 1 to 2 thin layers in moving air, and that has a corrective factor of 0.9. So you want to be very careful. Make sure you not only correctly get the number of layers and whether they're thin or thick, but also the condition of the air, and of course whether the clothing is dry or wet. So we tend to focus on dry clothing in this course because it tends to be the more common and the easier thing to deal with. But in the real world, as I said, things are messy. Sometimes the body's dumped in a river or a lake, and so if you find it quickly enough that you can even apply these algor mortis type of postmortem interval calculations, then again, you have to take into account that the body heat is lost very, very quickly. Okay, so now that we know what the corrective factor is for one thin layer of clothing in still air, we now have to know what to do with it. And actually the place that it goes is you take the body mass in kilograms and you multiply it by the corrective factor. So in this case, when we take that 81.8 kilograms, put it over 1 just to make it a fraction like students tend to enjoy, and we multiply it by 1.1, which is the corrective factor. It doesn't have a unit. We're going to stay in kilograms. We end up with now 90.0 kilograms. So that looks more normal, right? There's a 90 arc. I do try to make things work out as best as they can for you. Maybe not always easy, but easier. And so we see in this case, we end up with 90 kilograms, and we would have been wrong to round down to the 80 kilogram arc when we got that body mass of 81.8, because as we saw, if you look at that 80 arc, that's really just about 29 and a half hours, or 29 hours anyway, and then some change. Instead, if we move just to the 90 arc, look at that, we're at roughly 33 hours. So it makes a big difference, about 4 hours difference there. And I'm not that kind. I won't give that kind of tolerance, and you'll likely in a multiple choice type setting have that option. So just be careful. Make sure you remember to check for corrective factors, and if that body is found in any state other than naked and still air, make sure to multiply the body mass in kilograms by the correct corrective factor. Okay, so again, by our nomogram or nomograph, this person appears to have died just about 33 hours ago. So my PMI is going to be approximately 33.0. If your line's a little higher or a little lower, you might be at 32.8 or 33.1. Like I said, there I will give a half an hour either way. So anything from, say, 32.5 up to 33.5 would be acceptable, but I'm not so kind as to give you something less than 30, which would be where you end up if you drew the line and then read off the 80 kilogram arc. Now we were wise enough, at least in this example, to remember to multiply the body mass in kilograms by the corrective factor. The other thing we have to consider is the postmortem interval is not just a single time. It's an interval, a range of times. So based on where we ended up, our region of this nomogram, we have to consider the plus or minus hours. And in this case, since we used corrective factors and we end up far to the right in the nomogram, we're actually at plus or minus 7.0 hours. If we were just naked and still air, we would be plus or minus 4.5, but because we had the thin layer of clothing, we're going to be at plus or minus 7.0 hours for our post-mortem interval. Okay, so now that we know that we have to add and subtract that 7.0 hours, again, an acceptable PMI would be 33.0 plus or minus 7.0 hours. But if we really want a good feel for that range, we go ahead and subtract the 7.0 hours and then add 7.0 hours to that original value of 33.0, and we end up with a range of times from as little as 26.0 hours elapsing since the time of death up to as much as 40.0 hours elapsing since this victim passed. So again, as more time passes and the victim body becomes cooler, it gets more difficult to pinpoint that post-mortem interval. So we have a much wider range here in example 2 than we did in example 1. Now, because things get messy in the real world and we don't always end up with the ability to read off an arc, right? Not everyone ends up to be 70 or 80 or 90 kilograms. At the very bottom of the nomogram, you can see that there's an expression for death time, T, where you can solve for it with some fairly involved math, again, a little more involved than most of us want to get at this introductory level. There's the exponentials and all that sort of fractional work. And so instead of using that, that's why we use the nomogram, and hopefully you like it. It's quick and easy and fun. But in the real world, spreadsheet software that has that sort of equation set is much more common. It's universally used. Nobody's using nomograms for criminal investigations these days. They're using that sort of thing. But it was an important historical piece, and it like I said, if nothing else, it's fun. Now, the nomogram that we used is good for temperatures up to 23 degrees Celsius. There are other nomograms that could be used for higher temperatures, and I show here on this slide an example of a nomogram that's good for ambient temperatures above 23 degrees Celsius, goes all the way up to 35 degrees Celsius. That's getting pretty close to 100 degrees Fahrenheit, so unless we're dealing with a body that's in a very warm place, this nomogram should cover anything beyond 23 degrees Celsius that the other nomogram couldn't account for. A reason I bring this up is because those nomogram practice problems on Blackboard, which I hope you will try, I hope you feel comfortable enough with the concept now that you don't feel you need to, but just to practice them, just to be sure, I would love to have you download that file and work on those and then check your answers against the answer key. The one thing to be aware of is some of those involve ambient temperatures above 23 degrees Celsius, and therefore you would need to use this graph, which is also available as a download on Blackboard under the Chapter 2 folder. So we more commonly use the one up to 23 degrees Celsius, which we use for both our examples here in this video, but just realize there are other ones out there, and there's even some problems that we have on our Blackboard site that involve the above 23 degrees Celsius variety. So hopefully you've enjoyed this and you feel much more confident now. But either way, I think the nomogram is, if nothing else, it's a fun way to apply the idea of body loss with time relating to post-mortem interval.